Okay, good day, everyone. We will get started in a second. So, any question before we get started? All right. Okay. So, just one quick thing. One of the classmates want to make up the test number one, so you can go ahead and make it up, right? That's all. Yeah, it's available now. Okay, for your test number one. Okay, and all right. So we will continue where we left off from last class. So we're gonna look at chapter one. So go to Blackboard, open a textbook, turn to page 73. And we're gonna go over the even problems in the back of your exercise section 3.1. So we left from last time. Okay. And we're gonna look at question 12, 14, and 16. Okay. All right, so first of all, read the question really quickly, and let me remind you what we're dealing with from last class. So basically, we learned a compound interest formula. So ending balance equal to principal times 1 plus interest, annual interest rate over number of compounding period over nt raised to nt, right? And here again, P represent principal, and rate, R represent annual interest rate, N is the number of compounding period per year, compounding per year. And also T is time years. So basically just learning one formula, right? This is the main formula we focus on in terms of dealing with the compound interest. Okay, so now look at question 12. So how much money will be in account yielding 3.09% interest compounded weekly? So the compounding period is compounded weekly. If $7,800 is deposited for 5.5 years. So if you go over the question, and we'll be able to find out some of the given information here. This 3.09% is annual interest rate, 3.09%. So that's given. So basically, turn into a decimal 0.0309. And we are also given this principal, right? 7,800 as a principal. So P is given $7,800. And then time T is given 5.5 years. Okay. And the number of compounding period, that's also given because it's compounding weekly. So that means number of compounding period is 52 per year. Okay. So basically we know all four pieces of information. Then you can just plug into the compound interest formula to get an ending balance. So A equal to P times 1 plus R over N to the NT. But again, throwing all the numbers, principal is 7,800 multiplied by 1 plus annual interest rate is 0.0309 over 52. And 5.5 years, 5.5 years. Okay, so this exponent is 52. Number of compoundings per year times 5.5. Okay. Then one thing you can do is you can calculate this in Excel or in the calculator, whichever you prefer. So I'm going to show you how to get a result in Excel. So I'm going to open Excel program. You can also do that. You can also try it in your calculator, right? Definitely. Okay. I'll share the screen with you. Here you go. So 7,800 multiplied by 1 plus 0.0309 and by 12, no, by 52. Okay. and then raised to exponent is 52 times 5.5. And that should give you the result right away, right? So if you hit enter, you get a result. So it's $9,244.45 if you run it to 2 decimal places. So the ending balance is $9,244.45. That's the final answer for question 12. $9,244.45. Okay. Any question on question 12? All right, so now let's take a look at question 14. Read the question really quickly. At what interest rate compounded daily will $5,000 grow to $8,000 in 7 years and 5 months? Okay. All right, so here definitely we're looking for the interest rate, meaning R is not known, right? R is unknown. We're looking for that. And we know the compounding periods because it's compounding daily, so that N equals 365. Okay. And we also know the principal. Principal is $5,000. Ending balance is $8,000. And then the time t is also given, 7 years and then 5 months. So you turn into a fraction, mixed number, right? 7 and 5 over 12 years. And typically you can turn into improper fraction by multiply the whole number, denominator. 7 times 12 is 84. 84 adding 5 is 89 over 12 years. Okay. Then we get time t, we get all of this, then we are actually solving for rate. So first of all, let's throw all of this into the compound interest formula. 1 plus R over N to NT. So throwing on the numbers here. So 8,000 equal 5,000 times 1 plus R is not known, but N is 365. Okay. And the exponent is 365 times 89 over 12. The reason why I didn't divide into didn't keep as a decimal number because 5 by 12 is not the well-run answer. So we'll keep answer as accurate as possible. So here we have this set up. Now next thing is we try to solve for R. All right, so first of all, we're dividing 5,000 from both sides of the equation. So we cancel 5,000 on the right. And 8,000 by 5,000, actually, that's, you can divide into that, it's 1.6. That's where I'm running answer, right, like that. 1 plus R over 365. And we can simplify this exponent, right, by multiplying 365 by 89 and divide by 12. And if you, okay, 365 times 89, okay, so it's 32. So we're still gonna keep it, we multiply 365 by 89, you get 32,485 by 12, okay. So now the reason I do that, because to make it slightly easier to move forward. So right here, we're gonna isolate, so reverse order, put a variable on the right, of the 365 raised to 32,485 by 12. Then on the right, it's 1.6. Now we need to get rid of this exponent here. So you're going to raise to the reciprocal power. So here reciprocal power over 365 raised to 32,485 by 12. And the reciprocal of this is 12 over 32,485. On the right, we do the same thing. 1.6 raised to 12 over 32,485. Okay. And this So using the exponent property, if you have a to the x raised to the y power, it becomes axy, right? And when you multiply these two reciprocal numbers, it becomes 1. Then get rid of the exponent. So we end up with 1 plus r over 365 on the left, and then 1.6 raised to 12 over 32,485. The next step is get r over 365 by itself, subtract 1 from both sides of the equation. Okay, we get r over 365. Okay, and that's equal to 1.6 raised to 12 over 32,485 minus 1. Then in order to get rid of the denominator, you multiply by 365 from both sides of the equation. Okay, we cancel the number, I is by itself. Okay, so now I is equal to this. So we put into the cell to get a result. Open parentheses, it's 1.6 raised to, and put the exponent in the parentheses, 12 by 32,485. Okay, and minus 1. Now we close parentheses and then multiply by 365. And that will give us the answer, right? Once you hit enter. And the rate is, we run it through 4 decimal places. Okay, so it's 0.0634. So 0.0634. 0.0634. Okay, so that's about 6.34%. Yeah. Any question on this? And that's question 14. And let's look at question 16. Again, this is a quick exercise reviewing the formula we learned from last Wednesday. And question 16, we have a how much will the money be in account if $7,500 is kept on deposit in account for 10 years, 3 months at 8 3/8% interest compounding monthly. So you're looking for the ending balance, will, right? Will means it's in the future. So you're talking about future value of the, so this is ending balance we're talking about. Now we're given the principal, right? Principal is $7,500, and time t is given is 10 years, 3 months. So 10 years, 3 months, you turn into a fraction, it's 3/12. And here it's easy to convert it as a decimal because 3/12 is 0.25, it's a quarter. So it's 10.25 years. Okay. And the reason why I don't keep it as a fraction because you can turn into a decimal with the well running numbers. Okay. Then we get t. Now the rate is also given. It's 8 3/8%. We turn into a decimal is 8.375%. Now we turn, again, we convert it back to decimal is 0.08375. Okay, so get a rate, get a time t, get a principal. We know the compounding period, it's compounding daily, no monthly. That means n equal to 12. Okay, so now once we know all of this, then plug into the formula p times 1 plus r over n to n t. All right. So now throw your numbers into the formula. So 7,500 times 1 plus, the rate is 0.08375 by 12. Now the exponent is 12 times 12 then 10.25. Okay, so easily we can use Excel to get a result. Okay, let's go back here. So you get 7,500 times 1 plus 0.0. Let me see, number really quickly. 8375, 0.08375. 0.08375 divided by 12 and raised to exponent. And make sure you put an exponent in parentheses because exponent itself is an operation. So it's multiplication operation. So 12 times 10.25. Okay. And that should be the proper input into the Excel. And once you have this, and key enter, right, get a result. So you end up with the $17,643.35. That should be the final answer. So 17,643.35. Okay. And so this again, the most important thing is summarize what you have from the question and then try to figure out what we're looking for. That's the key thing here. And let's take a look at question 18 and 20, right? So for your assignment from section 3.1, you can stop at 21. So you don't have to go beyond 21, right? After 21 is optional. So if you want to do it, do it. If not, that's okay. You're obligated to complete up to question 21. Okay, so I will wrap up this by going over 18 and 20. Okay. Maybe I'll give you some time to look at these two questions before we go over the answer. 80 and 20, right? Give you a couple minutes, look at it, and try to use the formula to solve it. And we quickly take attendance. Okay. Okay, so let's look at question 18. Anybody want to share your opinion or your answer on question 18? What are we looking for here?
The principal?
Exactly, very good. So now, right, that is indication is principal. That's not known. What's given here?
The amount?
Okay, great. Arisa. Yes, it is, right? We're looking for the amount. Okay, amount is 65,000, right? And what else is given?
The time, 17 years, and the rate?
Very good. 17 years and rate. Perfect. 438%. Very good. And then typically we turn the rate into a decimal numbers. So it's 4.375%. And also that becomes 0.04375, right? And one last thing we need is it's compounded monthly, right? So number of compounding period is 12 per year. Okay, and then once you have 4 elements, remember we have 5 variables in the formula. If we know 4 of them, then we can find out the missing one. So here, so ending balance is given. Principal is what we're looking for. And then again, we're going to throw in your numbers into the formula. So you get 65,000 here equal principal times 1 plus. This is 0.04375 by 12 and raised to 12 times 17. And we can get a very running numbers here for the exponent. If you want to simplify that, feel free to do so. 12 by 17, that turned out to be 204. So the exponent here is 204. Okay, we'll go from here. So 65,000 equal to principal times 1 plus 0.04375 by 12 and 204. And in order to get P by itself, we're just dividing both sides of the equation by the exponent. 1 plus 0.04375 by 12 raised to 204th power on both sides of the equation. 0.04375 by 12 raised to 204. Now again, we get rid of that term here. Principal is by itself, and then principal becomes, we write it as 65,000 over 1 plus 0.04375 over 12 raised to 204th power. Okay, and I'm gonna quickly show you how to do this in Excel. 375 200. Okay, there we go. I put here. So we get 65,000. That's numerator, and divide by denominator. Put in the parentheses first. Okay, and then we divide by open parenthesis for denominator. 1 plus 0.04375 divided by 12 and raised to 204th power. And once you do that, and then close parentheses. And this is complete input. And then here enter, you get a result, right? So that should be $30,938.14. If you want to deposit that amount of money, you end up with $65,000 in 17 years. So if you look at the amount, it's more than doubling, right? It's slightly more than doubling, which is pretty good. So $30,938.14. So we're looking for different things, right? Previous one, we're looking for rate. We're looking for ending balance, beginning balance, the principal, and also sometimes we may looking for the time t, right? That's also possible. Let's see if the last question is about the time t. Let's look at it. Okay, question 20. How long? Yeah, it is about time t. So we actually cover all the cases here. We looking for how long, meaning time t is not known, right? And we know the beginning balance principal is 3,800, right? And I grow to 10,500. That's a ending balance, $10,500. The rate is given. Is 4.45%. When you go decimal, 0.0445. And we also know compounding period, which is weekly, meaning 52 weeks in a given year. Now we have all 4 elements. And the only thing we don't know is time t, right? So 5 variables, if you know 4 of them, then the missing one we'll be able to figure out that. So ending balance equal to principal times 1 plus r over n to nt. And again, we're still working with the same formula. So ending balance is 10,500. The principal is 3,800 times 1 plus 0.0445 over 52. And then time t, we don't know. Yeah, so 52t. Okay. And you want to get rid of this coefficient. So we're dividing 3,800 from both sides of the equation first. It's for the first step. Cancel that. Now you can drop 2 zeros, right? Same amount of 0. Drop that and reverse order. Here we're gonna get 1 plus 0.0445 over 12 over 52 raised to 52t. And the right is 105 over 38. Now, so what do we do after that? Anybody remember? In order to isolate a t, what do we do? Okay, so taking Ln from both sides of the equation, right? Just like the other one. When we're talking about the population growth, we actually perform similar operation at 0.0445 and dividing by 52 raised to 52t. So basically taking Ln from both sides of the equation. And in terms of equation, when you perform the operation on one side of the equation, then you have to perform the exact same thing on the other side of the equation. So to keep it balanced. So this is a very important piece of information. Okay, so now 52t goes in front. Okay, so now we separate them. 52t times Ln of this 1 plus 0.0445 over 52. On the right is Ln of 105 over 38. Now eventually, we need to get rid of 52 and Ln. So dividing both sides of the equation by 52 times Ln of 1 plus 0.0445 over 52. Same thing on the right, 52 times Ln of 1 plus 0.0445 over 52. Okay, cancel 52, cancel Ln, and t is by itself, and t is what we're looking for. So t is equal to that. Let's see what that is. But again, I'm going to show you how to perform this operation in Excel. So it's going to be Ln equal to Ln and 105 over 38. That's numerator, and dividing by denominator, open parentheses, 52 times Ln of 1 plus 0.0445 by 52. Okay, now once you input it properly, then we'll be able to get a result right away. Yeah, let's see what that is. Just hit enter, get a result. Okay, so it's about 22.8, right? So you can just run it to 1 decimal, that's okay. So 22.8 years and 22.8 years. And from there, I think they want to ask us to convert it to report your answer in years and weeks, nearest weeks. So we know that it's going to be 22 years and multiplied by 0.8 by 52 weeks. And we get 22 years, 0.8 times 52 and that turned out to be 41.6 weeks. And they want to run it to exact weeks, so that should be approximately 22 years and 42 weeks. All right. So that's how you will run it to the whole week, right? 22 years, 42 weeks. Any questions on this? All right, and so we wrap up the exercise in the back of, again, you are obligated to complete up to question 21, right? You don't have to complete the rest of the question if you don't want to. Meaning 23, 25, and 27, you could just skip it, okay? As your homework assignment. All right, I'm gonna get started on the new section today, section 3.2. And basically we continue, it's built based on the section 3.1 compound interest formula, but we look at more interesting cases, compounding in different compounding period. Okay, so now I want you to open the PowerPoint from 3.2. And we're going to talk about continuous compounding, effective interest rate, and also the bond pricing in section 3.2. But one thing at a time, right? We're going to talk about the, first of all, let's look at the continuous compounding formulas and how we derive the continuous compounding formula. I will show you that in a second. Share the screen. Here we go. Okay. All right, so first major topic in section 3.2 is continuous compounding, then effective interest rate, and the bond pricing. Three major topics. And let's look at the continuous compounding formula first. So this is the formula we learned from the section 3.1, right? We call this compound interest formula. So the continuous compounding formula actually comes from the compound interest formula. And we already know of this. P is principal amount, N is number of compounding period, R is annual interest rate, time is 20 in years, right? So we know all of this. And to develop the equation, determine the continuous compounding interest, that we're assuming principal equal to $1, right? And then R equal to 100%, time t equal to 1. And that N approaches infinity. And if you look at the next table, you will see what we talk about, right? But remember that P is 1, rate is 100%, time t is 1 year. That's assumptions we are making here. Now let's move on to the next table. So first of all, yearly. Under the compounding yearly, number P is 1, right? Rate is 1, and then time t is 1. Okay, that's all 1. So if it's compounding yearly, that means N equal to 1. So we apply the compound interest formula. Let's see what is the ending balance here. So it'll be 1 times 1 plus, the rate is 1 over 1 to the 1 times 1, right? So that's basically give us 1 times 2 to the first power. So this is 1 times 2, give us 2. So that means ending balance is 2 if it is compounded yearly. And if it is compounded quarterly, that means N equal to 4. All right, so let's try that. Okay, so here principal is 1 times 1 plus, now compounding here is 4, so 1 over 4, quarter, right? And N is 4 times 1. Okay, so this is basically 1 times 1.25 raised to the 4th power. And we could easily find this in Excel, so let me double check. Let me show you how to get this in Excel. Okay, so we do 1 times 1.25 raised to 4th power. Okay, this turned out to be 2.441406. 2.441406. So 2.44 441406. Now I want you to finish the rest of them, right? So if it's a compounding monthly, compounding daily, compounding hourly, and this is a given compounding period. So monthly n equal 12, daily 365, hourly 8. It could be secondly, right? It could be compounded by minutes, compounded by seconds. Now the n become much bigger, right? Okay. Try this 3, see what you end up with. And you will see how this continuous compounding was developed. I'll give you a couple minutes, quickly calculate all these 3. All right, so let's look at the monthly, daily, and hourly compounding. So still we follow same formula, 1 plus 1 times 1 times 1 plus 1 over 12, and then it will be 12 times 1. So it will be 1 times 1 plus 1 over 12 to the 12th power. Now one more time, if you throw into the Excel, it will be 1 times 1 plus 1 over 12 raised to 12 power, and it becomes 2.613035. 2.613035. 2.603. 2.613035. 3035. Okay. As you can see, this actually become bigger and bigger, right? So that's a trend. If it is compounded daily, that will be 1 times 1 over 1 plus 1 over 365, and dividing by 365 times 1. And this is going to be 1 plus 1 over 365 to 365th power. If you do not want to write a 1 in the front, you can omit it. That's not needed. So all we have to do is we do equal to 1 plus 1 over 365 raised to 365th power. Now that becomes 2.714567. 2.714567. Now we're gonna move on, right? So to the hourly, and you want minutes, right? How many minutes in a given year? You can just multiply this by 60 minutes, right? That we multiply this hour, 8760 by 60 minutes to get total minutes. Also seconds, multiply by another 60, then get seconds, and then that's how you, if you want to move forward. But let's see, 8760, and this is 8760 compounded hourly, meaning you receive interest 8,760 times over a year times 1. So it becomes 1 plus 1 over 8760 raised to 8760 power. And one more time, let's calculate in Excel. So 1 plus 1 over 8760 raised to 8760. And then he enter, right? So you get a result. So it's 2.718. Now you see that it's getting an older number. So older number. We call that natural number, 2.718, 127, 2.718, 127. And this is getting closer to this. And if assuming n is approaching infinity, infinity, this case indicating compounding continuously. So if it is compounding continuously, meaning n approaches infinity, then this becomes e, older number, right? Compounding continuously. And e is what we call natural number or older number. The mathematician who discovered this using this procedure and with a formal proof is called Euler. It's a Sweden mathematician. Also, it's called natural number. We use this in population growth examples, right? The population growth is compounded continuously, meaning population increases or decreases on a continuous basis. Same thing here. I'm going to show you something, some real example in the financial world, which is also compounded continuously. Okay, so 1 second, let me show you that right now. If you go to Google, if you type in, let me share the screen. Yes. You just type in national debt, and this is one of the real world example, about the continuous compounding. I just want to show you the feature of what happened to continuous compounding. Okay, national debt clock, right? 2020, no, 2021, right? And you can go to this organization called National US Debt Clock. And if you click on it, and you look at this number right here, this is US national debt, right? So currently, if you look at it, every second is going up, although it's going up by a little bit, right? But still it's going up. So this is a key feature of the continuous compounding, meaning you are earning interest infinitely many times in a given second. Okay, and if you look at it, this is about 28 trillions already. And yeah, that's basically, this is a real-time clock, right? So that means this interest is compounded continuously. That's why it's keep going up every second pass by. And this is very typical example of continuous compounding. And it actually comes from the compound interest formula, right? This continuous compounding formula. Now let's keep going. All right. So we actually come up with this Iona number. So within logs. So basically, when n approaches infinity here, if you simplify what we did in the table, this limit will approach e, which is 2.718281828, right? It's just like pi. E is like pi. It has infinitely many decimal places. referred to as natural base. Okay. And logarithm with base e is called a natural logarithm, ln, right? We've been using this, but they actually come from this order number or natural number. Any question on this? How to derive the order number? You can also derive yourself, right? Very easily, you just keep going using the table, just keep increasing the n, right? Give a bigger n, keep going, and eventually you will arrive at a very close number to this, to the one we show here. Okay, then we actually already learned how to graph the exponential function with the base e, right? So basically you just pick some x values, remember -2, we actually do -2, -1, 0, 1, 2, right? And you find the y values by plugging into the this exponent with base e. Then we get all these numbers and then you can plot it, right, from the graph here. So you see, this is the graph, right? The point of given all the pairs. -1 corresponds to 0.37. So this -1 here, get that point. And then 0 is 1, right here. And then 1 is 2.72 is right here. And as you can see, 2 is 7.39. So go up here. And you're connecting all those 4 points, and then you get this exponential function with base e. Yeah. You extend it in both directions. And here, x-axis is what we call the horizontal asymptote. And the inverse function of this is what we call ln of x, right? So this is symmetry line. Y equal to x is symmetry line. Inverse function, basically, the y becomes x, x becomes y. So this is basically the essential characteristics of the inverse functions. And we get all these points symmetrical with respect to, if you draw this, they are symmetrical with respect to the symmetry line here, y equal to x. Then you get all these 4 points. Now you connect it, you get the inverse function. We call this ln of x. This graph for the ln of x also extending both directions. And if you look at it for the mirror image based on the symmetry line, y equal to x. Okay. And yeah, that's inverse function of natural logarithm will be the inverse function of an exponent with base e is natural logarithm function. Okay. So then they are inverse of each other. This is f(-1) of x is called inverse function of f of x. And then inverse, that's why we have this ln of e to the x. It becomes x, right? Because they offset each other. Natural logarithm and then exponents with base e, they are inverse function. They undo each other. That's why the answer is turned out to be x. Also e, if you have ln of x, you become exponent and then natural logarithm, they undo each other, it becomes x. It's because of the inverse nature. Okay. And again, you probably see this a lot in the algebra course, and we just review this really quickly. So the continuous compounding formula actually comes from this. So it's basic principal times natural logarithm with base e raised to RT. Okay, so we know A is ending balance, right? And then P is principal, I is annual interest rate, T is time T. Okay, and there's a formula here to use in terms of continuous compounding. And let's take a look at how we apply this formula to do an actual calculation here. So that's assuming you have $1,000 deposit into a treasury account, right? Just like The national debt actually it's borrowed by the Federal Reserve, right? Federal Reserve. So basically, if you lend $1,000 to Federal Reserve, so the Federal Reserve into the Treasury bond, right? And you get paid continuously in terms of interest. So this is how that works, how the national debt works. Basically, Federal Reserve borrow money from the investors, and they pay investors on a continuous basis. Now you have $1,000, right? Let's say you lend it to the Federal Reserve, and they tell you that they're going to pay you 5% compounded continuously. So this is very important. You have to see this word compounded continuously to know we can have to apply this. Now, how much will be in the account after 10 years? And again, we have formula here. All we have to do is figure out what's given here. So this $1,000 is initial investment. You can also call that principal. So principal is $1,000. Okay, and then we know the interest rate, which is 5%. Okay, and turn into 0.05 decimal numbers. And time t is 10 years. And we know that's continuous compounding. So in this continuous compounding formula, we only have 4 variables. E is not counted as a variable, right? So I only have 4 variables here. If you know 3 of them, you'll be able to find out the missing one. And the missing one here is ending balance. Okay. So all we have to do is throwing all numbers into the formula. So we get A equal to principal times e to the RT. So it's principal, which is $1,000 times E. Rate is 0.05 times 10. And again, you have to use either calculator or Excel to do this. And let me show you how to get this in Excel really quickly. So you just have to do this. So you get $1,000 times EXP, right? That's exponent with base E, EXP. And put an exponent in the parentheses. So exponent is, let's see, 0.05 times 10. 0.05 times 10. All right, so once you input it like this EXP represents E raised to this power, E raised to this power. Then the result turned out to be $1,648.72 after this time. So $1,648.72. So the ending balance is $1,648.72. Okay, and that's how you deal with this continuous compounding problem. And the formula actually is even simpler compared to the compound interest formula, right? Because of the nature of this. But this actually continuous compounding method is the best among all other compounding methods because you receive interest infinitely many times over the life of the time. Okay, of the life of the loan. Okay, so this is the best option. So if you offer different investment return options, continuous compounding is always the best. Okay. Any question on this? Now let's move on to next question. Question number 2. How much should be deposited in an account yielding 4.3% compounded continuously so that we will have $100,000 in 10 years and 10 months? Okay. Anybody want to give an opinion? What are we looking for here?
Principal?
Exactly, right? That should be deposited. Exactly. How much? Right now, right? So basically, you're looking for principal. Okay. And what's given here? we know this interest rate, right? The rate is given 4 and then 38%. Okay, that's given. So it's 4.3785%. And then turn your decimal is 0.04375. We know that thing. And we will have $100,000, right? So that's ending balance is given 100,000. And then time t is also given 10 years and then 10 months. And basically we're going to turn into a fraction. So it's 10 and 10 over 12. Okay. So we can turn time t into a fraction. And here you go. So we just simplify this. If you turn into a improper fraction, that'll be 10 times 12, 120, adding 10, 130 by 12. Okay. And now we're looking for p. So apply the formula p times e to the rt. I just have to plug in all the numbers into the formula. So 100,000, that's ending balance, equal principal times e, and the rate is 0.04375 times this. Time t is in fraction, 130 by 12. Okay. Now basically you just have to get rid of this exponent on both sides of the equation by dividing e. And if you want to multiply this by 130 and turn it into a single number, we can do that. Let's see what that is. 0.04375 times 130, and about let's see what that is. 5.6875. So if you want to simplify this and turn it into a single number, you can do that. 0.04375 times 130 by 12. We divide both sides of the equation by that exponent. Okay, and if you get rid of that, then p is by itself. So p is the quotient of that, 100,000. And you multiply this number by 130, and this turned out to be e raised to 5.6875 over 12. Okay. Now once you simplify to this extent, then we go into the Excel. So you get 100,000 dividing by exp, right? E raised to exp, open parentheses, and it's 5.6875 dividing by 12. 5.6875 by 12. Okay, and now if you input it correctly, then just hit enter and get a result. So it turned out to be $62,353.32. That means that's your initial investment. Once you put in the initial investment, then you get the final result. So $62,253.32. So this is approximately $62,000. $253.32. $260.32. Okay, and that's your initial investment in order to achieve this goal. In 10 years, it's like almost doubling your money, right? Based on this rate, compounding continuously. Now, question 3. So pretty straightforward. How long, right? Meaning you're looking for t. T is not known. Will it take from 9,000 to grow to 15,000 at a 4 1/8% compounding continuously? Okay. So one more time, principal is given 9,000. And then ending balance is given 15,000. Interest rate that's given is 4 1/8%. This is 4.125%. And the decimal is 0.04125. Okay. Now we know 3 things. The only thing we don't know is time t. Let's solve for it. So a equals p times e to the rt. It's 0.041. Yeah. Let me just write out the formula first. RT. Now, next step is just plug in the numbers. 15,000 equal to 9,000 times the R is 0.04125 times t, and we're solving for t, for solving for time t. And now first step, I'm dividing 9,000 from both side equation. If you simplify that, 15,000 by 9,000 actually is 5/3. Right? You can simplify into a simple fraction, 5/3. Drop the zeros and then simplify further. Here we get e raised to 0.04125 times t. Then reverse the order, write e first, 0.04125 t equal to 5/3. And how do we proceed? How do we get rid of the base? E.
ln.
Exactly, right? So taking ln from both side equation, very good. Ln of the whole thing, 0.04125 t. Ln on the right hand side do the same thing, ln of 5/3. Now ln and e offset each other, they undo each other. So end up with 0.04125 t equal to ln of 5/3. So the very last thing, dividing both side equation by the decimal number 0.04125. Okay, now we got it, right? T is by itself. So use either Excel or calculator, quickly find out the result. So it's ln of 5/3 by 0.04125. So we do ln 5/3 undivided by 0.04125. Yeah. Okay, so and then if you just hit enter, you will get a result. Okay, so that turned out to be above 12.4 years. Right? If you run to one decimal place, so it takes about 12.4 years to reach the goal. So whatever we end up with the time t, right? The unit is always years. Okay, and you want to convert back, I mean, to more detailed time, you can do that. Right? 10.4 as a month, and then days. We're going to do that. That's doable. And example 4, at what interest rate? So definitely, what interest rate you're looking for R? Right? Compounding continuously, and will $7,500 grow to $12,000 in 7 years and 7 months. So principal is given, P is 7,500, ending balance 12,000. Then time t is given 7 years and 7 months. So if you turn this as a fraction, it will be 7 and 7/12. Okay. Then we get all these three. The only thing we don't know is interest rate. So we will use a continuous compounding formula. Before that, right, we can turn this as a x improper fraction. 7 times 12 is 84. Adding 7 is 91/12. Now make it slightly easier when we move forward into the RT. And one more time, three numbers: 12,000, 7,500 times E. R is what we're looking for, 91/12. And here we're solving for R. So first of all, dividing 7,500 from both sides of the equation. Cancel that. Then we can drop the 2 zeros, right, if you want to. So it becomes 120 by 75. So E raised to 91/12 R equal to 120/75. Now from there, we will take in the ln from both side equation. Okay. Then the ln and exponents of AC, they offset each other. 91 over 12 times R equal to ln of 120 over 75. And you multiply this by the reciprocal, so multiply by 12 over 91 from both side equation. Okay, and this reciprocal offset each other, right, becomes 1. So I is by itself. So all we have to do is multiply these two. Get the result, we get an interest rate. So one more time, put it here. We multiply this ln of 120 by 75. Okay. And multiply by 12 over 91. Okay. And that should give us the proper answer. This turned out to be 4 decimal place, run them to 0.00620. 0.0620. That's the answer. 0.0620. And if you turn into percentage, it will be 6.20%. That will be the percentage we're talking about. Okay. So now let's quickly do the exercise. Right? I want you really to practice this. So let's go to the textbook. Yep, so turn to the textbook, right? And then let's move on to exercise from section 3.2. Go there. Okay. All right. Now just look at question 2 and then question 4. 2 and 4. Continuous compounding, right? And question 4, yeah, continuous compounding, but you're looking for interest rate. Okay. So I give you a couple minutes, work on those two. All right, so let's look at question number 2. So you're looking for how much, right? How much meaning we're looking for the principal, because will be $100,000 in account after 11 years, 5 months, and interest rate is given. So we're looking for the initial investment, or you can call that principal. Principal is unknown here. The rate is given 3.99%, and ending balance 100,000. Time t is also given 11 years and then 5 months. Typically, we will turn into a fraction. So it's 11, 5 over 12. Now, next thing is turn into an improper fraction. 11 times 12 is 132. 132 times 12 adding 5 over 12. 11 by 12, it's 132. So 132 adding 5 is 137. So now once you know all 3 of them, then we'll be able to solve for P. So ending balance equal principal times e to the RT. Okay. And you have to check the keyword, right? Continuous compounding. That must be presented. And 100,000 equal to principal. R is 3.99% is 0.0399. So 0.0399 times 137 by 12. You want to multiply these two, right? We can do that just to simplify a little bit first before we move forward. So 0.0399 times 137 becomes 5.4663. So I'll get 100,000 equal principal times 5.4663 by 12. Now solving for P, so you just have to divide both sides of the equation by this exponent. So dividing E with 5.4663 by 12. E raised to 5.4663 by 12. And we cancel the exponent by AC, and P is by itself, so P equal to 100,000 raised to E 5.4663 by 12. And let's see what the present value is by throwing into the Excel. And let's see what that is. So it's 100,000 divided by EXP 5.4663 divided by 12. Okay. And that should give us the result. Just hit enter. You get $63,411.50. That should be the initial investment or principal. You put it down. 63,000. $411.50. And that's a question 2. Question 4. And what interest rate? So definitely we're looking for the interest rate. The money grew from $98,789 to $123,822 in 15 years and 11 months, assuming continuous compounding. Initial investment or principal $98,789. Ending balance $123,822. Time t is also given 15 years, 11 months. So this is 15 and 11 over 12. Again, we turn into an improper fraction. 15 times 12 adding 11 divided by 12. 15 times 12 is 180, adding 11, 191 by 12. 191 over 12. This is very important, right? You have to do the conversion, before we get started. And let's apply the formula A equal to principal times e to the RT. So ending balance 123,822. Principal is 98,789. As E. I is what we're looking for. We know the T is 191 by 12. Step 1, we will get rid of the 98,789 from both sides of the equation. So dividing 98,789 from both sides of the equation, so cancel the coefficient. So get an E 191 over 12T. 123,822 divided by 98,789. And we're taking the LM from both sides of the equation first. LM, the whole thing. These two offset each other. And here's LN of 23,822 over 98,789.
Professor, instead of T, it would be R, right?
Oh, yeah, you're right. Yes, definitely. You're totally right. Yeah, I overlooked. I write down the wrong thing. Yes, the R is missing. T is given, right? Definitely. We're not solving for T. We are solving for R. Very good. Catch. So let me just quickly erase those. Okay, let me erase this. And also that. Okay. And let's see. All right, so let me just get a background. Yeah. Okay, so yes, that's what we're looking for. So now here, these two offset each other, and E, so we get 191 over 12 times R. Okay, then Ln of this whole thing, 123,822 over 98,789. And then we use a reciprocal. So reciprocal is 12 over 191. Multiply that to both sides of the equation. Okay. And our reciprocal, right, cancel each other. Yes. I is by itself. And we just have to simplify this. Okay, get the result. Okay, so let's put into Excel. So here go Ln of 122,000. 23,822 by 23,822 by 78,987. Yeah. Let me check. 789. 80,789. 789. So we have that, and dividing by, multiply by 12 over 191. Okay, and that's proper input. And once you hit enter, you get a result. And let me double check the number one more time. Okay, the number is good. Okay, here you go. So the answer is 0.0142. So we keep it as 4 decimal places. 0.0142. That's the rate we're looking for. 0.0142. So that means it's 1.42%. Compounding continuously. And yeah, that's really what we're looking for. Now let's look at question 6, right? I want you to quickly look at question 6. I'll give you a couple minutes to try that first. So after 10 years, 57,000 grows to 96,500. And account continues compounding. How long will it take money to double in this account? So again, it's a doubling problem. So give a shot. Right? Anybody want to share your answer to this?
Professor, I have a question over here.
Definitely, yeah.
I don't know if my answer is right, but if I get like a decimal amount, do they want us to show the years and the month or just like the month?
Yes, years and then months, right? Yeah.
Okay.
Okay, so all right, so that means most of you guys probably finished. So first part of the question, after 10 years, this 57,000 grow to 96,500. From there, you'll be able to find out the rate, right? So the rate is not known here. Rate is unknown. We're looking for that. So time t is given 10 years. The beginning balance is 57,000. Ending balance is 96,500. And we're solving for rate. And once you know the rate, we'll be able to solve doubling problem. But we have to get to the rate first. So here we go, ending balance equal principal times e to the RT. Okay, and just have to throw in both numbers, 96,500 equal to 57,000 times e. And then the rate we're solving for that, time t we know is 10. Okay. And first of all, we dividing 57,000 from both sides equation. So then we cancel that coefficient 57,000, drop this both zeros, right? So we become 965 over 570. So e to 10r equals to 965 over 570. And again, we're taking the LM from both side equation, then go from there. So ln of e raised to 10r equal to ln of 965 raised to 570. Now simplify ln and e offset each other. 10r goes in the front. 10r equal to ln of 965 over 570. And from the very last thing, we're dividing 10 from both side equation. Drop the 10, r is equal to this. And then here you're going to keep as many decimal as possible, because r is not what we're looking for. We're looking for the doubling time. We try to keep it as accurate as possible. So here we do ln of 965 over 570, yeah, 570, and then divide by 10. Okay, and whatever decimal we have here, we're going to copy the whole thing, right? 965. Yeah, okay, got it. So now we just hit enter, and let's get a rate. And the rate turned out to be 0.052649, right? At least 6 decimal. That's very minimal already, right? Let's go back here. And the rate turned out to be, yes, 0.052649. Okay. And again, you want to keep as is. Do not run it, right? Because this is an intermediate result. We not only want a rate, we also want a doubling time. Now, step 1, step 2, we're going to look for the doubling time. So again, you can assume for doubling time, initial balance is, principal is $1, right? 1 unit, and ending balance will be 2 units. And we know the rate, copy the whole thing, 0.052649. And all we need to do is solve for time t, doubling time. One more time, you apply the formula A equals P times e to the RT. I will throw in on numbers 2 equal to 1 times e, and rate is 0.052649 t times t. And then we can omit that 1, right? And just basically e raised to 0.052649 t, that is equal to 2. Now from there, we're taking the ln from both side equation, okay, ln of 2 on the right, and simplify, get 0.052649 t equal ln of 2. Now solving for time t, dividing both side equation by 0.052649. 0.052649, and cancel that time t by itself. Yeah. And we just divide ln of 2 by the decimal number we have. So ln of 2 by 0.052649. 52649. We end up with 13.165. So if you run it to 2 decimal place, no, 1 decimal, right? 13.2 years. So that would be the proper answer here. 13.2 years. If you want to turn it into months, so it's going to be 13 years. So 0.2 times 12, that'll be 2.4, right? 2.4 months. And that's so 13 years, 30 years, 2.4 months. Again, you know, you usually just run it to 13 years and 2 months. But for a regular running rules, when you so just drop down to 2 months. All right. Any question on this? Yeah, so let's continue our lecture. So actually, the next question is about the APR, right? So let's look at the APR, how we deal with the APR. APR is the effective interest rate. So let's go back to the PowerPoint. So next thing is basically when you try, let's say get a loan, get a car loan or mortgage from the bank will give you a rate, right? Typically, if you go to, let's say you open a saving account or checking account, and the bank will always give a rate. Let's say the saving account rate right now is very low, it's less than 1%. That's assuming 1%, right? So you go to bank tell you if you deposit your money in the bank, you receive 1% interest. And that 1% being given, being offered to you, that's what they call a nominal interest rate. Okay. Nominal interest rate is like face value. So whatever they offer you is a face value, right? And if you want to know the actual effective interest rate is the actual interest rate, meaning you got to look at a compounding period. And actual interest rate is always, it's also called APR, annual percentage rate, right? Or annual percentage yield. So API is actual interest rate. It's what they call the effective interest rate, because effective interest rate consider the compounding period. So if the bank tell you it's 1% compounding monthly, the actual interest rate is more than 1%. Okay. Well, if you borrow the money from the bank, right, for your car loan, then let's say it's 1%, then 1% compounding monthly. At the end of the day, you pay more than 1%, and that's what they call the actual interest rate. So let's look at this example. Let's say we have 18% compounding monthly. Okay, so this is the nominal interest rate, right? Nominal interest rate is 18%. Okay, and since it's there's a compounding period associated with it, and that means interest period is compounding monthly. So monthly compounding here. So we're going to utilize this monthly compounding thing to get an annual percentage rate, right? Which is what they call APR. So which is actual interest rate. It's going to be slightly more than 18%. You'll see in a second. So basically, this is just conversion between the nominal interest rate and then the APR, right? That's what we learned for this topic. And this 18% compounding monthly, what it really means is interest rate per month is 18% by 12. So it's 1.5% per month. But remember, the interest you earn from the first month, it will generate interest for the second month and then the upcoming months. That means that for the second month, the interest rate will be slightly higher compared to the first month. And the number of compounding period, interest compounding period is 12. Those two are important. So the bank will charge 1.5% interest each month on your unpaid balance. So if you borrow money, and you will earn 1.5 interest each month on your remaining balance if you deposit money. So that's basically depends on whether you lend money to the bank or you borrow money from the bank. Two scenarios, right? but still they're going to charge 1.5% interest on the remaining balance. And this is what they use to find out effective annual interest rate, effective interest rate, or APR. And we're using this I with a subscript E to represent the effective interest rate. And you can also call this actual interest rate. If you look at the borrowing side, it's actually the real borrowing cost, right? Compared to 18%, it's going to be slightly bigger than 18%. So that means you're paying slightly more than 18%, paying more. And once you figure out the APR, the effective interest rate. So basically, this is a formula we utilize. So I is a nominal interest rate per year. I with the subscript E is effective annual interest rate. You can also call that APR. And then N represents number of compounding period. So the effective interest rate is the same as APR. And now let's look at it, -1, right? So it's formula is 1 plus R over N to the N minus 1, assuming it's 1 year, right? So here, because it's by default, time t equal to 1 year for the simplification purpose. So time t equal to 1. So now let's look at this. Still the 18% compounding monthly case. Suppose you invest $1, right, for 1 year at 18% compounding monthly, how much interest would you earn? Now let's calculate that, right? Using compound interest formula, or you can use effective interest rate formula. How much interest would you earn? So we do ending balance first, right? P times 1 plus R over N to NT. Okay. So using compound interest formula, so P is $1, right? Time t equal to 1. Okay. And the rate is 18%, which is 0.18. Okay. Then we pretty much N equal to 12, right? It's compounding monthly. So now we move all of these, plug into the formula. So here we go. So you get 1 times 1 plus rate is 0.18 over 12 raised to 12 times 1. Okay. And so this is basically 1 plus 0.18 by 12. Well, actually, it's right around the answer. So if you want to turn it into a decimal number, no problem. 0.015 raised to 12 power. So now let's use Excel to get this. So this is going to be 1 plus 0.015 raised to the 12th power. As you can see, running to, let's say, to how many decimal is initial, 18%. So now let's run it to 3 decimal place. Okay. So it turned out to be 1.196. So the ending balance in this account will be $1, approximately 1.196. So, and then if you look at the rate, actual borrowing cost, right? The rate, effective interest rate, should be the ending balance minus beginning balance over the beginning balance. So basically, it's going to be 1.196 minus 1. Initial balance is 1 divided by 1. So this turned out to be 0.196 by 1. So it's 0.196. 0.196, that's 19.6%. So the actual borrowing cost, or API, is actually 19.6% instead of 18% of the nominal rate, right? So this is just using compound interest formula to get that. If we use the formula we just talked about, right, we can get a rate right away. So I of E equal to 1 plus R over N to the N minus 1. So basically, we just plug in all the numbers. So it's 0.18 over 12 to the 12 minus 1. So this is 1.196. minus 1, that turned out to be 0.196. So this turned out to be 19.6%. So using the formula, right? Talk about from previous or using the compound interest formula, we learned to get the ending balance and using the ending balance minus beginning balance divided by the beginning balance, that gives us the actual interest rate or effective interest rate. And they turn out to be the same result. Okay. So now 1.5% per month, if you look at it, this is approximately 19.6. We got that. So it's 19.6% compounding annually. That means the actual interest rate here, the actual interest you pay into the bank or bank paying to you will be 19.6%. So that's how we utilize this compound interest concept to figure out the actual interest rate. Do you have any question on this? So the nominal rate, the nominal interest rate actually does not give us the accurate amount in terms of borrowing cost. Nominal interest rate is like the face value, right? So you usually don't take the face value. You perform the calculation yourself and figure out the actual borrowing cost or actual lending cost, right? Something like that, using the APR. Now think about this. If your credit card calculates interest based on 12.5% nominal interest rate, so you have a credit card. Credit card works in a very similar way. What is your monthly interest rate, and then what is annual effective interest rate, respectively? Okay, how do we find out the monthly interest rate? So monthly interest rate, you're just dividing this nominal rate by 12, right? So monthly interest rate is equal to 12.5% divided by 12. Okay, so this is 0.125 by 12. We'll be turning into a decimal number, 0.125 by 12. This is approximately 0.0104. Okay. So that's about 1.04% on a monthly basis. And in terms of finding the effective interest rate, so you apply the formula here. So effective interest rate, i.e. equal to 1 plus R over N to N minus 1. So here this compounding monthly, right? So credit card also is compounding monthly because you are paying interest on a monthly basis. So that's why it's compounding monthly. So this is going to be 1 plus rate is annual interest rate is 12.5%, is 0.125 over 12. The 12 power minus 1. And let's see what that is. So again, you just have to plug into the Excel or the formula sheet. Then let's get the results. So 1 plus 0.125 over 12 raised to 12 power minus 1. Okay. And then the result here is 0.1324. So if you run it to 4 decimal place. Yeah, so it's 0.1324. So the actual interest rate is 0.1324. Meaning that's going to be 13.24%. Okay. So so that's going to be the effective interest rate, right? So this is the APR, actual borrowing cost. Okay. So actually the credit card company is charging you 13.24% APR instead of a nominal rate of 12.5%. So in essence, you're paying more towards your credit card account. Right. Any question on this? All right. So I think I will stop here today. And this Friday, I have a meeting to attend, right? So I won't be able to make it to the class. So you guys, you don't have to join the class this Friday, and then you can just complete whatever project you haven't complete. And if you need extension, just let me know, right? Okay, so no class this Friday. All right.
Okay, thank you,
Okay,
Professor.
no problem, guys.
Have a good day.
Okay, have a nice day, guys. Bye.
Bye.
Talk to you guys next Wednesday. Bye-bye.